So in this problem, we're given velocity components u and w, and we're asked to solve for the velocity component v. What we're going to see here is that this is an example of the application of the equation of continuity for an incompressible fluid. So let's get started. So we're given really the major assumption that we have to apply here. So we're going to assume that we have an incompressible fluid. And in this case, this is a question about the distribution of velocities within the fluid, which is a really good hint that what we're looking at here, what we should be looking at here, is the differential form of, our balance equations. In this case, we don't actually have to make an assumption about whether the fluid is Newtonian or really anything else, but we can just start with this assumption that we have an incompressible fluid. I will further, I suppose here, make the assumption that this is steady state, meaning d dt is equal to 0. And with these assumptions in place, we're then going to write out expression del dot v is equal to 0, which is our statement of incompressible continuity. This is, without knowing exactly the direction to go in the solution method, this is a good place to start because it's going to help show a relationship among our different velocity components. And since we know u and we know w, we just don't know v, this expression is going to help us find what we're looking for, which is v. Okay, so let's write out this expression. So incompressible continuity del dot v is equal to 0 is equivalent to saying that du dx plus dv dy plus dw dz is equal to 0. V is unknown, u and w are both known, so we can start to plug these in. So du dx, that's going to be the derivative of, let's write it out, d of a times x squared minus y squared dx plus dv dy plus derivative of b dz is equal to 0. And we'll see that the derivative of b, a constant, with respect, b is a constant, with respect to z, this is just going to be 0. And this term here is just going to resolve to 2 times a x plus dv dy is equal to 0. So we can rewrite this as dv dy is equal to minus 2ax. And now simply to find the form of v, what we're going to do is just integrate this, right? And we can write this out as the integral dv, or we're going to say, sorry, v is equal to the integral of minus 2ax dy. Therefore, v is equal to minus 2ax y plus a constant. And maybe the trickiest part of this here is that this constant is really just a constant with respect to y. We don't really know anything else about its dependence in x, z, or t. And so we can write this out in general as some constant c that's a function of x, z, and t. And if we go back up here to our statement of continuity, we can see that essentially any function that is only a function of x, z, and t would still satisfy this expression, because this term here, so any function here, anything we plug in that's a function of x, z, or t, would still have partial derivative with respect to y that's equal to 0, and so it would not contribute to this incompressible continuity expression. And so this is going to be the most complete form of our final answer. Um, that was really just an application of the equation of incompressible continuity to find an